the difference of textbooks here. So let's take a look at, when we're talking about addition rules and multiplication rules, what those rules look like with probability. So one of the things that we need to understand when we're working with probability is how are those events, compared to each other. So when we talk about two events that are mutually exclusive or disjoint events, we're basically saying they cannot occur at the same time. So like over here, they talk about an example. What if the person is female, the person is Republican, the person is both female and Republican? So yeah, this can happen at the same time, right? The person can be a female and they can still be Republican. However, if you look at the second example here, we're saying the person is a Democrat and the person is an independent. Now, this cannot happen at the same time, right? You either identify yourself as a supporter of the Democratic Party, or you say I'm an independent, so I don't, go with either of the two parties. So this event could not happen at the same time. Whereas being a female and being a Republican, yeah, that can happen at the same time. So the second example where they're talking about being a Democrat or being an independent is what we would call as mutually exclusive or disjoint events, because they cannot happen at the same time. And then, you've got a couple different examples over here where they're asking us to determine if the two events are mutually exclusive or not. So I'm actually going to hide. Okay, looks like Naomi is having some trouble. Are the rest of you having trouble with Zoom? Either not able to hear me or see me? Because every now and then I know my internet gets a little bit slow. So I don't know, Naomi, if the issue is happening at my end or is it happening at yours? Oh, I do keep freezing then. Interesting. Okay, so it might be happening at my end, Naomi, then. Let me just very quickly check what my router is saying about my internet connection. Just give me a second here, guys. Okay, so right now it is showing full connection, but I apologize, guys, if that keeps going in and out. Yeah, so right now it's showing it's looking good. So let's hope it will, keep it that way. Okay, so let's take a look at these examples here. Like I said, we'll kind of hide the answers for now so we can, look at it ourselves before we see what the answers are. So this one is just talking about, determine whether the two events are mutually exclusive. And so here we are saying selecting a female student and selecting a student who is a junior. So can these two events happen at the same time? And if they can happen at the same time, then they are not mutually exclusive. If the two events cannot happen at the same time, then we say they are disjoint or mutually exclusive. So what do you think? Can you be a female student and a junior at the same time?
Absolutely.
Absolutely, yeah. So that tells us these are not mutually exclusive. Well, you get the spelling. Okay, the second example is saying selecting a person with type A blood and selecting a person with type O blood. So can these two events happen at the same time?
No.
No, because you're either going to be type A or type O, right? So that means this is definitely an example of, yes, these are, mutually exclusive. Alrighty, perfect. So they're saying rolling a die and getting an odd number, rolling a die and getting a number less than 3, which means when you roll a die, can you get an odd number which can also be less than 3 at the same time?
Yes.
What number do you think that would be?
1.
Yeah, so 1 would satisfy both of these because 1 would be an odd number and 1, of course, is also less than 3. So obviously that means these guys are not mutually exclusive. Okay, very good. Randomly selecting a person who is under 21 years of age and randomly selecting a person who is over 30 years of age. Can that happen at the same time? No, I see Naomi shaking your head. So yeah, you were either going to be under 21, maybe in between or over 30, but you cannot be, you know, obviously 2 different ages at the same time. So this one would be definitely, yes, a mutually exclusive, you know, events. And like I said, you can kind of look at the answer and explanation here if you wanted to. So that is actually something that we have to be thinking about, you know, when we are trying to consider the probabilities and how to calculate them, because then you will see when we talk about events being mutually exclusive. So when 2 events, A and B, are mutually exclusive, then this is going to be your addition rule for mutually exclusive events. Okay. When the events are not mutually exclusive, and you can see again, they're using Venn diagrams to show us the difference. So basically you can see there's no overlap between the 2 circles, because if there was overlap, then, you know, you would see circles like this where this area would be common between the 2 circles. So since there's no overlap, we're saying these are what we call as mutually exclusive events because they're not happening at the same time. And you've got several examples that I've got in here for you to look through. But if events are not mutually exclusive, then you will see how different this rule is a little bit, because here you will see you're adding each of the individual probabilities, right? So we're adding probability of A with probability of B, but then we are subtracting the probability of A and B, and that A and B represents that intersecting portion. So we're saying take the probability of A, which is the entire circle, take the probability of B and add them together. But then because this portion is getting counted with A and B, you're actually counting this twice. So that's why we go ahead and subtract it to, you know, count it only once. So that's what your addition rule looks like when your events are not mutually exclusive. So you will see with mutually exclusive, you just had to take probability of A, add that with probability of B. But then with not mutually exclusive, we have to subtract that probability of A and B. And that is something we always have to, you know, consider when you are talking about probability for any event as such over here. So let's see if I can find us an example to look through for this guy. Okay. Yeah, we can do this. Let's look at number 31 over here. So this is talking about using a standard deck of cards. And I guess they have a figure on page 246 if you wanted to see what the standard deck of cards, I guess, looks like. What page are we on? 252. Okay, so there you go. That's what a standard deck of cards would look like. So just as a quick review, you can see they're starting with ace on each of the suit. They go with 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have what we call as the face cards, the jack, king, and queen in there. So that's for each of those four suits. So you've got spades, hearts, clubs, and diamonds. So you can kind of see what that breakdown looks like. So keeping this, we'll go back to our number 31 here. Okay, so the first one they are saying, of course, they're saying one card is randomly selected from the deck. So compute the probability of randomly selecting a heart or a club from our deck of cards. So what is the probability that the one card we selected will be a heart or a club? So this is where we first have to think about, are they mutually exclusive events? Can one card be a heart and a club at the same time? No, right? Because they're two different suits. So obviously there will be no overlap. So since these are mutually exclusive events, that means you can use that first rule of probability here. So that means to find out if the card is going to be a heart or a club, you will add the probability of a heart with the probability of a club, and that will give us our total, probability over here. So I'm just actually going to do this right over here. So let's think about how many hearts are there in a deck of cards? Because
Well,
each suit has how many?
13.
32.
That's for the whole deck. And then how many of them are hearts? Dennis, you were saying something.
13?
13, yeah. So the entire deck of cards, and we can call them, our size for the universal set or for, the sample space is 52. You have 13 in each suit. So hearts will be 13 out of 52. And okay, Darla, I just saw your answer. And it's going to be the same thing for clubs, because a club is also a full suit. So you will have 13 out of 52 for the clubs also. So when they're asking us what is the probability that the one card we select is going to be both, could be a heart or a club, you add both of those probabilities together. And as you can see, this will come out to be, and this is, where our little exercise on those fractions comes into play. So will it be a heart or a club is going to be adding the two fractions together. And so can you tell me what our total will come out to be here?
26.
Okay, and then as a reduced fraction, what are we looking at, guys?
1/2.
Yeah, because 26 out of 52 is, obviously you're looking at two suits out of the four of them. So yeah, you have basically a probability of 0.5 or 1/2 that the card you select could be a heart or a club. So that will be our part A over here. Alrighty, very nice. And then let's look at what happens with part B. So first thing again, are these going to be mutually exclusive events? This is saying compute the probability of randomly selecting a heart or club or diamond from a deck of cards. So technically, we've actually already done the probability of heart or club. What is the probability that the card will be a diamond? And again, are these mutually exclusive to each other, or can you have any overlap between a heart, club, and diamond?
Mutually exclusive.
Yeah, so these guys are also mutually exclusive because the diamond is also a suit of cards, right? So there's going to be no overlap in these events either. It's honestly just an extension of part A, They're just bringing in the suit of diamonds in here. So these are also mutually exclusive events. And so for this guy, and well, I guess we'll need to go back over here. For part B, you will actually do, can it be a heart or club or diamond? So again, in this case, you're adding each of these individual probabilities with no overlap. We don't have to subtract anything. So again, these are all suits, guys. So that would be 13 out of 52 as a probability for each individual set. And what kind of total are we looking at here?
$39 over $52.
Yeah, very good. And again, we will be able to reduce this down. So what would be common between 39 and 52?
0.75.
Yeah, actually 13 is common between both of them. So this will reduce down to 3/4, or as Dennis mentioned, in a decimal, of course, you're looking at 0.75, which I guess this guy as a decimal could be 0.5, because it's, you're looking at 3 out of the 4 suits, so 3/4. Okay, so these were all mutually exclusive events. Now let's see if part C is the same thing. They're saying compute the probability of randomly selecting an ace or a heart from a deck of cards. So an ace or a heart. So can these be occurring at the same time, or are these mutually exclusive? An ace and a heart.
They can occur at the same time.
Yeah, because we can have an ace of hearts, right? So these are not mutually exclusive events. Okay. So this formula is then going to be a little bit different, and let's take a look at what that will end up looking like. So I'm actually going to clear this out so we can see a little bit better over here. And let's get down to this guy. Part C, they want to know what's the probability that our card will be an ace or a heart. So since these are not mutually exclusive, that means you would take the probability of, what's the chance that we will get an ace, add that with the probability of getting a heart, but then we would have to subtract the probability where there's a possibility that ace and a heart can happen at the same time. So let me ask you this first. What is the probability of getting an ace? So how many cards in our deck of cards are an ace? Yeah, very nice, Darla. There's 4, right? Because each suit has an ace of its own. So you will have ace of spades, club, diamond, and heart. So there's going to be 4 of them. So that's 4 out of 52. We already know the probability of getting a heart is 13 out of 52. Now, how many cards in a deck of cards are both an ace and a heart? Just one, right? Ace of hearts? Yeah, so only one card, because that one card is being counted with the hearts. That same card is also being counted with the aces. So you want to remove that overlap, and that's where that subtraction comes in. And just to show you again, that's this formula we are looking at right over here. Okay. So what does this guy add up to then?
$16.50.
Yeah, very good. And then we will be able to reduce this guy down. And I know you can definitely reduce it down by a 2, but can we reduce it by anything higher than that?
By a 4.
Yeah, by a 4. So 4 will go into 16, of course, 4 times. 4 will go into 52 13 times. So this will come out to be 4 out of 13. Okay, so you can see how the formula changed when we had non-mutually exclusive events, and there you can see we had to subtract that common card between both our groups. But then with the other two parts, of course, they were mutually exclusive events, so we didn't have to worry about subtracting anything because they had nothing in common, between the two. Any questions on this example here, guys? Okay. So 2 addition rules based on if you have mutually exclusive events or not. And then again, you will see there's a whole bunch of different examples in here to, just to show you how with different scenarios those examples would work. So you can kind of look through them. Then we also have multiplication rules when we're talking about, calculating these probabilities. So with multiplication rules, we can say, again, you can find that probability for 2 or more events that occur in a sequence. So they're talking about, if you toss a coin and roll a die, what is the probability that you are going to get a head for the coin and, get a 4 when you roll the die. So basically, in this case, we then have to think about, are the 2 events independent, or does one event affect the other one? So if you think about this, tossing a coin is really not going to make a difference on how you roll a die. So in this case, the one event is not going to affect the other one. And so we say, yes, they are independent events. And they're saying 2 events, A and B, are independent events if the fact that A occurs does not affect the probability of B occurring. And in that case, if your 2 events are independent, then this is going to be our multiplication rule. So you take the probability for A and B, and to calculate that, you multiply probability of A with probability of B. So using that example of, the coin and the die, for the coin, you're going to have a sample space of 2 outcomes, right? Head and tail. With the die, we're going to have 6 outcomes, depending on which number it lands on. So if we wanted to know what's the probability that we will get a head on the coin and a 4 on the die, you can see we're using this multiplication rule over here. So you have head and tail, 2 outcomes, which means the probability of landing on a head is going to be 1/2 because that's 1 outcome out of these 2. Landing on a 4, that's 1 outcome from a total of 6. Out of 6, there's only one number where you have a 4. So you can see we're multiplying the 1/2 with the 1/6, and that gives us the probability of 1/12, or, as a decimal answer. And we looked at this sample space last time, when we used the tree diagram. So you basically already have the sample space with you, and you can think about this. If we use the entire sample space, there's only 1 outcome from the 12 where you get a head and a 4, and you can see that's this outcome over here. So out of 12, only 1 of them is going to give us a head and a 4, and you can see that matches when we did our probability, just by using this formula over here. So that's kind of what they're showing you if the events are independent. Now, what happens if you have dependent events? Okay, so to understand what dependency is, let's look at this. They're saying, suppose a card is drawn from a deck and it is not replaced, which means you don't put the card back into your deck of cards. And then keeping that card outside, you draw a second card. This is where you will see dependency happening. So we are saying when the outcome or occurrence of the first event affects the outcome or occurrence of the second event in such a way that the probability is changed, the events are said to be dependent events. And then again, they're listing out, an example over here. Same thing, drawing a card from a deck of cards, not replacing it. If you have an urn with balls in it, if you take one ball out, don't replace it, and then select the second ball, kind of the same thing with cards. Here they're talking about two events which would be dependents. If you're a lifeguard, getting a suntan is part of that, because if you're going to be outside sitting all day, obviously you're going to get a suntan. So that's a dependent event. Having high grades and getting a scholarship. So yeah, high grades can usually lead to a scholarship. So that can be dependent events. Parking where you're not supposed to park. So parking in a no parking zone and getting a parking ticket would again be dependent events. So what happens in this case is then your probability changes as you calculate. So they're talking about, let's say, we're talking about what are the chances that we get an ace the first time we draw a card, right? So we know there are 4 aces in a deck of cards. That probability will be 4 out of 52. Now, what are the chances that we can get a king on the second draw? But remember, if we picked whatever card we picked for that first draw, we did not put it back in the deck. So that means when you draw your second card, you only have 51 cards in your deck now, not 52. So you will see that probability for a king, even though you still have 4 kings left in your deck of cards, your total number of cards in the deck is only 51 because you didn't replace that first card. So you will see how this probability changes. So, of course, that means this answer is going to change. So this is what they are talking about as being dependent events and how that changes your probability. So they're saying the event of getting a king on the second draw, given that an ace was drawn on the first time, is what we call as a conditional probability. And they actually go through a little more description over here for the conditional probability, but you will see when we talk about calculating probability for dependent events, see how that formula changes a little bit. So with independent events, you just had to multiply the probability of event A with the probability of event B, right? This was independent events. For dependent events, you actually have to use conditional probability. So you are multiplying probability of A with probability of B, given that probability of A already happened and it has affected the probability of your second draw or second event, which is dependent on it. So they're talking about the notation for conditional probability is this one here. It's definitely not division. You're not dividing anything here. It just means that event B occurs given that event A has already happened, or the event A has already occurred, which in this case, remember, for the kings, your probability changed because we did not put that first card back into our deck of cards. So that's what it means by conditional probability. So let's see. Well, you've got a whole different types of examples over here. This one actually also talks about if you had to calculate your conditional probability, what that formula would look like. So P, probability of A and B basically divided by probability of A. This is actually just rewriting the second multiplication rule. They're just rearranging it. So to calculate the conditional probability, just take probability of A and divide it on the left-hand side. And that's basically how they come up with this conditional probability formula here. So again, you can see a bunch of examples to help you out with that, but let's find something in our textbook over here.
So a quick question.
Yeah, go ahead.
Say on event A, we drew a king and did not replace it.
Yeah.
So therefore, we still have 51 cards. Would that change the second fraction to 3 out of 51? Or is that set ahead of time?
Very nice. All right. Very good, Dennis. That's a good question. So you are drawing a king on both the first and second draw?
No, you're figuring out the odds of getting an ace on the first one, but your first draw didn't happen to be an ace, that we're assuming that there's still 4 kings out of the 51 cards left.
Okay, I
Let's
see what
say
you're
instead
saying.
of drawing an ace, we drew a king, now knowing there's only 3 out of 51 left.
Okay, and I don't know why my video got turned off, probably when I was having trouble with my internet. So what's happening here is this is almost kind of leaning towards classical probability, Dennis. So what we are saying is you haven't actually drawn the card from a deck yet. We're just saying, what is the probability that you draw the first card as an ace? So we know that's going to be 4 out of 52. Now we are assuming that you drew an ace. And then we are saying, okay, so now what is the probability that you are going to draw a king on the second one? So the idea is the king hasn't been drawn yet. You still have 4 kings left behind, but obviously only 51 cards left behind since we didn't replace, this card was not replaced. Now, however, if you were going to be drawing kings on both the first and the second draw, so that would affect your probability, because if we are drawing king on the first and second draw, well, for the first one, yes, we have full deck of cards and we have all 4 kings. Now, the idea is you again are not replacing the card. But now we're saying, okay, what if this card was a king? You did get the king out, which means you now only have 3 kings left behind and only 51 cards left in your deck. So in this case, if you were drawing the same card in first and second, then you see how much more that second probability changes. But if you're doing like 2 different cards, an ace and a king, the assumption is, we got the ace on the first draw. Now, what happens when we get a king on the second one?
Okay,
it's
so
not
this is
so
all
much of like
based
a-
on assumption, not an actual, the second variable is affected by the actual results of the first variable.
Yeah, because we're just wanting to know what are the chances, or like you said, what are the odds, is what we're interested in. But, obviously, practically the first time you draw a card, it would very good chance it's not going to be an ace or a king, right? It could just be any other card in there. So this is just, more of a assumption or hypothetical situation of what if we wanted an ace on the first one and a king on the second one? What are my chances?
Got it.
Okay, wonderful. So let's see something with it's gotta tell us it's not replacing or something, so we know it's going to be dependent. Okay, these are more generic examples. Well, even with the card examples, I'm not seeing if they're telling us did they put the cards back or not. Well, anyway, we'll take a look at this next set of examples over here. So let's get into 33. So they're specifically asking us to exclude the leap year from these calculations. They're asking about computing the probability that a randomly selected person does not have a birthday on November 8th. This one is actually getting into complementary. Let's look at that. I think that might help us with this. Do they show that over here? Okay, this is with the employees. These were counting rules. Okay, so they're actually talking about how we can use probabilities of multiplication rules to help us calculate, probabilities of an at least event along with complementary event rule, which we saw in 4.1. There we go. So remember, we had talked about complementary events as basically anything that is part of your sample space, but it's not part of the event E or event A, or whatever the case might be. So in this example where we're talking about what is the probability that a randomly selected person does not have a birthday on November 8th, you kind of have to think about, okay, what is the probability that a person could have a birthday on November 8th? So take a second and think about this. What is the probability that a person could have a birthday on this given date? How would we calculate that?
1 out of 365.
Very nice, because that's one day, one date out of 365 dates. So we know the probability of having a birthday on November 8th, and we'll come back over here. So the probability that the person could have their birthday on November 8th is 1 out of 365. So if we had to find the probability of not having a birthday on November 8th, this is where you want to use that complementary rule. So 1 minus 1 out of 365. And what will that end up giving us?
364.
Yeah, 364 days, which are all the other dates out of 365. So using that complementary rule, to help you find the probability over here. Okay. This guy was part A. Part B is saying compute the probability that a randomly selected person does not have a birthday on the first day of the month.
So you would subtract 12 from 365.
Which will give us
353.
353. Okay. Okay, so this one actually looks like an example using all complementary calculations over here, actually. Okay, so they do not have a birthday on the first of the month. So that's, of course, like you said, if we talk about probability of has a birthday on first of month, then that would, of course, be 12 out of 365. So if we're saying they do not have a birthday on the first of month, then same thing, using that complementary rule to help us calculate this, because otherwise you would have to do it the long way, which obviously does not seem like a practical way of doing that. So just again do the same thing. And I think, Dennis, you said 353.
Yes.
All righty. Will that be similar to part C, where they were asking us the birthday person does not have a birthday on the 31st of a month, or will it be a different calculation? Do all months have 31st, Darla?
No, February doesn't.
No,
Days?
only 7 months have 31 days.
Only 7 months have 31 days. Okay, so that would be your January, March, May, July and August are the only months, that are kind of consecutive. You can, I guess, make the argument with December and January also. So July and August. What am I missing? October and December?
I just sing the song and scratch them off the list. 30
You have a
days has
song?
Yeah, 30 days has September, April, June, and November. The rest have 31 with the exception of February.
Huh, nice. All righty, very good way to remember. So that means, again, same thing. We know 31st of the month is 7 months, so that's 7 days out of the year. So same thing, you would be doing not a birthday on 31st. So what does this total come out to be?
.019.
Okay.
358.
Thank you. That's what I was looking for.
Oh, I'm sorry.
That's okay.
Yeah, 358.
Okay, yeah, again, you're doing 365 minus 7, and that gives you the 358. Okay, and I think the last one said does not have a birthday, I believe, in December. Come on, buddy. What is the probability that the person was not born in December?
It would be 11 because, I mean, there's 11 months besides December, right? Or
It's 31 days off of 365 for the
Yeah,
month
so instead of
December.
months, we're just doing the calculation with days. So you just take away the number of days for December, and that would be your probability. So basically the idea is, if anybody's born in December, that's 31 days in December out of 365. So anybody who's not, born in December. So what does that end up looking like?
334.
334. Because you have 334 other days remaining when the person could be born, right? If they were not born in December. And this is going to be true. The 334 out of 365 is going to be true for any of those 7 months where you have 31 days. So, that probability will stay the same. So January, March, May, July, August, October, December, all of those months will have the same probability. Okay, guys, so this actually was not the example I was hoping that we could talk about. So let's just look at an example through your handout, because I just want to show what happens when you're working with these conditional or dependent events. So let's look at this, and we'll kind of hide the solution here for a second. So they're saying a box contains black chips and white chips. Oh, come on, buddy. There we go. Okay. And they are telling us a person will select 2 chips without replacement. So that means they're not putting the chips back into the box. Okay, so that's the crucial part over here. Then they are saying find if the probability of selecting a black and a white chip is 15 out of 56, and the probability of selecting a black chip on the first draw is 3 out of 8. Find the probability of selecting the white chip on the second draw, given that the first chip selected was a black chip. So basically we are saying, what is the possibility or probability that you would select a white chip when, or given that the first time you select the chip, it's going to be a black one, So this is where you're using this conditional probability formula. So this is what we're trying to find. So you have to do the probability of black and white divided by the probability of, selecting a black chip. So probability of selecting a black and white chip, and divide that by the probability of selecting a black chip. So you can see they're telling us the probability that we get a black and a white is 15 out of 56. So that will go on our numerator. So 15 out of 56. Oops. And then you're dividing this by the probability that we will draw a black chip on the first draw, which is 3/8. So you are taking 15 over 56 and then dividing it by 3/8. So, it's fractions in both numerator and denominator. And, of course, you can use the tricks of dividing a fraction by a fraction, which usually comes out to be, if you're dividing a fraction, let's say 15 over 56 by another fraction, 3/8, then remember this is where you invert your second fraction, change the multiplication to division, and then you can simplify it that way. Or, in this case, you can go with your calculator and try and see what the answer comes out to be, but you can see we're kind of highlighting that calculation right over here. And it will end up giving you the conditional probability that you will get a second draw of a white chip if the first one was a black chip as 5 out of 7 or 0.714. If you look at this example over here, this one is talking about the probability that Sam parks in a no parking zone and gets a parking ticket is 0.06. The probability that Sam cannot find a legal parking space and has to park in no parking zone is 0.2. So they're saying Sam arrives at school and he has to park in a no parking zone. What is the probability that he will get a ticket? So in this case, we are saying the probability that he will get a ticket when he parks in a no parking zone. So again, you're finding that conditional probability. So again, you will have to do this as parking in the no parking zone and getting a ticket. So that probability they're giving us as 0.06. And then you divide that by the probability of getting, not finding a parking space and parking in a no parking zone. And that probability is 0.2, which is also given to us. And then when you divide this, it will tell you what are the chances that he's going to end up getting a parking ticket. And you will see we don't really like to divide decimals by decimals, but since they're giving us a probability in decimals, we have no option but to do that. And you will see that's a 0.3 probability or a 30% chance that Sam's going to end up getting a parking ticket. I mean, yes, it's on a lower side, but I would say don't park in a no parking zone if you want to avoid the ticket 100%. So that's kind of how, working with these conditional probabilities or basically dependent events will look like. So you've got more examples here to kind of browse through and look over. So definitely, kind of look through those. You have this example with the at least probability. So, if you are finding, like this example here is talking about what is the probability that the person will get at least one heart, if you're selecting 3 cards and replacing each card in this case. So you are selecting 3 cards from a deck of cards, you're replacing them, and we want to know what's the probability that they will get at least 1 heart out of those 3 cards. So this is where you have to think about, okay, what my probabilities are going to be. The probability of this person getting no hearts. So this is kind of where they were talking about using this complementary events with multiplication rules. to help you find the probability for an at least type of event. So what is the probability that you get no hearts? And remember, we're replacing the card back, so our 52 cards will stay the same every time. So we have 13 cards which are hearts, which means 39 of them are not going to be hearts. So that's where this probability is coming from. So 39 out of 52 is for the first draw, 39 out of 52 is for the second draw, and 39 out of 52 is for the third draw. You can reduce your fractions if you like, 3/4, 3/4, 3/4, multiply them, and we get a probability of 27 out of 64. Now we want to know what is the probability that at least one of them will be a heart. And this actually should not have that bar on top of that. That's a typo. This should be 1 minus the probability that we do not get a heart, which is 27 out of 64. And you can see that comes out to be 37 out of 64, or 0.578, or 57.8%. So the chances of getting at least one heart when we draw 3 cards from a deck is going to be approximately 57.8%, which is still a relatively decent probability that out of the 3 cards you draw, one of them could be a heart. You've got other examples to help you out with those at least type of examples. So definitely, look through these examples. But what I wanted to do was actually walk you guys through our flip a coin example, because I wanted to give you, at least a week to work on it, because this will be due, next Wednesday. So this one is actually coming from a binomial experiment, and we haven't talked about binomial experiment yet, but the main things about a binomial experiment, as you can see, are going to be these 4 requirements. So the one thing we talk about is you have to have a fixed number of trials. So the number of times you do the experiment has to be fixed. Your trial can only have 2 outcomes. So you can think of those 2 outcomes as being success and failure. So, if you're talking about, tossing a coin, then it's very easy. You either get a head or a tail. That's 2 outcomes. If you're rolling a die and you're interested in one particular number, so let's say you're rolling a die and you only want to know how many times I'm going to get a 3 out of each roll that I get. So then you can say I get a 3 or not a 3, right? So we don't care if it's 1, 2, 4, 5, 6. You have a 3 or it's not a 3, right? So success and failure. So as long as you can take your outcomes and break them down into 2 possibilities, like I said, think of it as a success and failure, that's a binomial experiment. Additionally, the outcomes of each trial have to be independent of each other, which means, if you're rolling a die, flipping a coin, the one roll, the one flip cannot affect the second time you do it, right? So each event has to be independent, and your probability of success for each has to remain the same. So that means if you're flipping a coin, the chance of landing on a head or the chance of landing on a tail has to stay 1/2, right? It has to stay 0.5. If we are rolling a die, then the chances of landing on a 3 has to stay 1/6 every time we roll a die. If we're picking a card out of a deck of cards, then your probability of getting, and I'll just stick with Ace of Spades, has to be 1 out of 52, no matter how many times we try it. So with the deck of cards, the important part here for number 4 would be you have to make sure you replace the card every time, because if you don't replace it, then your probability is changing, right? And they're saying the probability has to stay the same for each trial. So if with the deck of cards, of course, we would have to make sure we put the card back. Or like we were talking about the black chip and the white chip example, that means you would have to put the chip back into the box so that your probability did not change. So these 4 requirements are very, very important, when we are working through binomial experiments. And then I've got some other examples in there to kind of just help you, understand what a binomial experiment would look like. And then based on that, we come up with the results you will have, we come up with a binomial distribution. So just like we had talked about, frequency, distribution with chapter 2. Think of in that same way, you can have a binomial distribution, coming from a binomial experiment. So that's what you guys are actually doing as part of this activity, is performing your own experiment with a coin. So, you're actually flipping a coin, recording how many times it lands on a head or how many times it lands on a tail. And then based on that, we will, do some calculations and then do some comparison with calculation. So I'm actually, since, if you are like me, then you probably never have change on you. So you can use a coin flipper, built into our random.org website. If you go to the homepage, you will see the coin flipper is, your third one over here. And so just click on that. Now, all you are doing is just flipping one coin, because, I was trying to keep this as simple as I could. You can select what coin you want. If you want to pick, you can see they're all from different countries, different types of coins. So if you want to do those, that's fine. All I would say is make sure you flip the coin a few times before you start recording your data, so you know what the head and the tail of that coin would look like. Because if it's a coin you're not familiar with, you may not know what is the head and what is the tail. For our purposes right now, you know what, let's just pick a quarter from Maryland. So you can see that's going to be the tail and that's going to be the head, right? We have George Washington on one side. Now, another thing I would ask you guys to be careful about as you're doing your coin flips, because a lot of times it's going to land on the head, or the tail. So how do you know your coin actually flipped? Look at that timestamp, because if that timestamp changes, your coin has flipped. So you can see my head did not change, but my timestamp did. So that's kind of what happens when you flip your coin. Sometimes you'll get the other side, but sometimes you'll just get the timestamp changing. So that's how you know your coin has flipped, when the time changes. So that's your coin flipper. If you don't have an actual coin, I would say if you have a coin lying around, use that. Now here is the worksheet where you will be recording your values. And so you will be flipping your coin 10 times. And you will repeat this experiment 3 times. So technically, you're flipping your coin 30 times, okay? Now, if you go to this spreadsheet, your template, and I've actually used this template, it looks like, for my other class. So I'm going to go ahead and remove these names for now. But you can see, I had everybody recording their answers, so I could kind of see what they had. So that's actually what I'm asking you guys to do right now. At least get, first 10 of your coin flips recorded. Now you will need to make a copy of this worksheet when you guys are working on your own, but for now I will go ahead and have you guys work on this same sheet that we are looking at right now. Let's change that to edit. So through the chat you will see this link coming through for this document here. But remember, when you guys start working on this assignment, you will need to make a copy of this or download it to your own computer to start working on the project. Right now, we're just doing this for class purposes, so you all get a chance to participate in this. So what I want you to do is, you can see I've got my first 2 as the examples here. I had actually used, if you just do Google search and type in flip a coin, it actually does give you a coin flipper, but you can see with the 3 experiments I did, I got 5 heads for each one of those. And I didn't like that because I wanted a little bit variation. So then I went to my random.org coin flipper, and you can see it gave me a better result because I've got 3, 4, and 5. So I liked that better. And that's the reason why I'm asking you guys to use the random.org coin flipper. Again, like I said, if you have a physical coin, that's fine. You can use that. But if not, just use the virtual one. So what I want you guys to do is you can see in all those yellow spaces, you can go ahead and put your own name in there. So just put your name so you know that's where you're working. And hopefully there are enough spaces for all of you, but I can go ahead and add a couple more rows just to make sure everybody has a space. So just pick one of those boxes, put your name in it, and use the coin flipper to get your, at least the first 10. And if we have time, we can do the others. But for now, just do the first 10. Coin flips record how many heads and tails you have. Okay, I think that should be good. I think I've taken all the other stuff out. Yeah, Allison, not a problem. Thank you for letting me know. So you're just recording what your coin flip looks like. So did you get a head or did you get a tail? That's what you are recording with these coin flips. And then I've actually already got a built-in function in there. So as you type your T's and your H, you will see under the number of successes column, it will already start adding those heads for you because we're only recording the number of heads. So heads is our success, tails is the failure. So remember the two outcomes, success or failure. And here you are counting your heads. Okay, so I can see some of you are already starting to put your answers in. So just get your first 10 coin flips in, and then I'll show you what the next part of the assignment is going to be. Okay, so I can see, Haley, you got 7 heads on the first experiment. Darla, you've got 4. Katya, you have 5. Let's see, Sabri, you have 4. John, you have 4 as well. Eliana, you've got 5. That's interesting. 4, 5 seem to be common values you guys are coming up with. Very interesting. I do see 7 with Haley, so that's a little bit of a variation. So that's nice. Wow, Jeffrey, you got 6 heads in a row. That's very interesting. Okay, let's see. Eliana, we've got 5 with you. Okay, Allison, looks like you came up with 6. Alize, you also have 6 on that first try. Okay. Dennis, you came up with 2. Okay, very nice. A little bit of a different number there. Okay, guys, so if you have your first 10 coin flips done, then you will see on that same worksheet, you have a second spreadsheet on the bottom. You will see it says binomial probability distribution. So that's where you want to go next. So that'll be the second page. And again, let's get rid of some of this data here. And I actually want to show you how these formulas work. So remember, one of the big things about our binomial probability distribution is that your probability has to stay for each trial. And you, of course, have to have the same number of trials for each experiment. So we did that by keeping 10 coin flips, for each experiment. So we're keeping our number of trials, the same for our experiment over here. So the next part, of our assignment is talking about after you record your heads, I am saying on the second worksheet of the same spreadsheet, you will complete the binomial distribution table using the binomial probability distribution function formula, and you will actually see that formula in section 6.2, and this will be based on how many heads you recorded on those 3 experiments that you performed. So in this handout right now, all you need to do is, again, just pick one of those squares, put your name on it, and then from that first trial that you did, how many heads do you have? Bring that number over. So you can see for my experiments, I had 3, 4, and 5. Since you guys only have one, experiment done, just bring that one number of head that you have so far. So just pick a table that I have in there and go ahead and put in your number of heads. And I've actually already included that binomial probability distribution formula over here. And then I've got an example right next to it to show you, how the formula will work. So the way the formula works is this is actually your combination formula. So you know how we have permutations and combinations? That's what this formula is over here. And I'm going to try and see if I can copy and paste it so I can kind of show you if it will let me. Oops. Okay. So this is the binomial, distribution formula we're talking about. So you have your combination formula over here. So the NCR is what combination looks like, but instead of R, we are using X. You multiply that with the probability of X and then 1 minus probability of N minus X. So this is that formula, and this helps us calculate, what is the probability based on the number of heads. So if you have 3 heads, which is what I had for my first experiment, that's going to be our X value, and you can kind of see that how I've broken this down. So we are doing this experiment, with 10 trials. So each time you are flipping your coin 10 times. So you can see I'm telling you here at the very top on this sheet that N represents the number of trials. So you can see right over here, I've got N as 10 trials, and that's what you did. You flipped your coin 10 times. So the N value for everyone is going to be 10. Then your X is going to be the number of success. So how many heads did you get? So your X represents the number of heads. So in this case, we would say, okay, so out of 10 trials, we got 3 heads. And then the P stands for what is the probability of success of each trial. So in your experiment, when you flipped a coin, what was the probability that you were going to get a head or a tail? And in this case, we're only interested in heads, right? So our probability is going to be 0.5 because the probability is 1 out of 2. So that p-value will also stay the same for everyone. So 0.5 for our p-value raised to how many heads you had. And then multiply that with 1 minus p, which of course, 1 minus 0.5 is also going to be 0.5. And then you are, as an exponent, you are doing 10 minus 3. So this is what you will need to calculate if you have, and I think one of you had 7 heads in there. So you would then be changing this to 10 because your trials stay the same, but now your number of heads is 7. So that means your probability is still 0.5 because you're still doing heads, but this number will change to 7. And then multiply that with 1 minus 0.5, and then the exponent will be whatever answer you get when you do 10 minus 7. So that's how you are actually calculating these. And I just wanted to show you for the combination, you can either find the NCR key in your calculators. On Desmos, I can show you that very quickly. If you go under function, you will see right over here on the bottom is your NCR. That's the function you are using. So if you were doing for my first experiment, which I had 3 heads out of 10 trials, you just have to type in, NCR and then 10,3, you get 120. So that will be for this first part over here. This answer comes out to be 120, and then multiply it with 0.5 to the 3rd power. 0.5, 10 minus 3 will be 7, so to the 7th power. So then multiply this with 0.5 raised to 3, and then multiply this with 0.5 raised to 7. And you can see I end up getting my probability that way. So this is what you guys will need to do for each of your number of heads that you come up with. And that's going to be your probability over here. So like for me, for the number 3, that would be the 0.117, whatever this number came out to be. So that, and since I've got my instructions in there, I'm just going to paste right next to it. But this is the value that should be right here next to my 3 and underneath my P of X column. So this is where I would be putting my, 0.11711875. So do you see how that formula works, guys, for the binomial probability distribution here? And I would say work with it. And if you get stuck, you can ask me next time. You still have time on Monday to ask me a question. So that is what you are doing for that first part of this assignment, is actually doing the coin flips, recording how many heads you got, and then using the formula to come up with your probability distribution table. And then you will actually be comparing it using this table. So those same probabilities that you are calculating with the formula, you will then compare with the table to see if you were right on track or not. So remember, our n value is 10. So you need to go down that first column and find where the n value will be 10. So it will be right here. You can see this is my n value of 10. Our x value will depend on, what your number of heads is. So I had 3 heads. And then remember, our probability of getting a head is 0.5 because that's 1 out of 2 outcomes. So then when I use that, you can see I am getting 0.117. And that's pretty close to what I had with my formula, because I had 0.117 and then, more digits after that. But you can see, yeah, it does a pretty good job of matching up to what I did with my formulas and what I got on my table. So definitely on the right path, with my calculations over here. So that's what I'm asking you in that second part, is to compare your answers from the formula to the distribution table. And you should see, is that going to be true for all of them or not? And why does that happen? So, you will do that comparison. And then after that, you will be calculating your mean and standard deviation, again, using 2 different formulas coming from 2 different sections of your chapter 6. So I would say at least get started on the first part of this assignment so that you get a chance to work with the formula and creating, this probability distribution table over here for the binomial. experiment. So if you have any questions on this, you can ask me that next time, and then we can get into, the next part of this assignment. So just please get a head start on that. And again, I will remind you guys to start working on your homework in my stat lab. If you haven't started on that, please start doing a little bit every day. So this time you don't fall behind, you don't miss an exam. That's our goal, to make sure you guys are ready for your exam then next Wednesday when it comes up, okay? So any questions before I let you guys go?
Can you show how the Desmos thing works again? Because mine's not working when I try and put mine in with the NCR. I don't know how to do that.
So select the NCR function, and then
Okay.
in parentheses, you will put your N value, which is going to be 10 because we're doing 10 trials. And then well, how many heads did you have?
7.
So you will do 10 comma 7 in the parentheses.
Okay. Okay. Thank you.
You got an answer?
Yeah.
Okay, awesome.
And
So
then I
you-
just use that instead for the equation.
Yeah, you can use that. And like I said, you
Okay.
also have in your calculators a built-in NCR function, but if you're using Desmos, that will work out just fine, not a problem.
Okay. Thank you.
Yeah, you're welcome. Any other questions coming to mind, guys?
When we do find the amount, do you want us to round it to a certain decimal, or do you just want us to put the entire total?
I think to be on the safe side, we can do 5 decimal places.
Sounds good.
Yeah, so that way it will stay even throughout. So yeah, go ahead and do 5 decimal places for your second column of that table, guys.
And then also, what are we comparing? Are we comparing the chart that you showed us to what we get on Desmos, or?
Yeah,
Well-
so your final answer from Desmos, which is what you're putting in that, second worksheet on your flip a coin template,
Mhm.
to the binomial distribution table, the table where you only have 3 decimal places answers given to you, you're comparing that to what you get from your calculator. Yeah.
Okay, sounds good. Thank you.
Yeah, very good. Good questions, guys. Anything else coming to mind? Okay. All right, guys. So this is where I will leave you, and then we'll pick up our discussion on Monday. So please let me know if you have any questions, okay? All right, everyone. Have a wonderful day. Be safe, and I will see you next week. Take care, everyone.
See you next week.
Yeah. Hey, Naomi, Darla, did you guys have a question?
Just a quick question that it's